Thank you. It's nice to be here this morning. My background is in intelligence systems. I'm in Singapore because we also, as a university, teach a security degree and a forensics degree in partnership with a local provider in Singapore at MDIS. As I said, my background is intelligence systems, and what I'd like to do today is to explain a little bit about what I do, and maybe if there are people that have got complementary skills, we could look and talk about maybe doing something together. That character, maybe some of you recognise him, some of you might not. That is Data. Data is a character from Star Trek, and really he is, in a sense, the ultimate data machine. He can do lots of the things that we can do. He can learn from information, he can see things, he can do things, and when you consider the kind of world that we live in, that's pretty impressive. Data is an android. That is, he's a mobile robot with a human form. I don't know. There's no sound there, I'm afraid, but what's happening is it's explaining who Data is. Data is an android. He has the ability to live in the world, to communicate, and to do some pretty amazing things. As you can see, when we look at data about Data, he's got some time before he comes into existence, but if we were to watch the video, you can see that he was created by humans. Now, we live in a world that is very complex, where people do not always say exactly what they mean, and yet we can understand what people mean by listening to what they say, and we can interpret it. Where we live in a world where the contradictory is often accepted and understood. Again, that's pretty complex. Where daft people do daft things. Where humans can determine the right meaning from many possible meanings. And humans survive in a complex world where even help is not always helpful. And yet we live in that world, and we survive in that world, and we thrive in that world. We live in a world where very few people are so straightforward as to have no secrets at all. And where things are not always as they seem. And yet we live there and we survive there. Where we understand words in a way that is not always easy to understand.
Like the entire power grid will all be burning the midnight oil. That would be inadvisable. Excuse me? If you attempt to ignite a petroleum product on this ship at 0-100 hours, you will activate the fire suppression system, which would seal off this entire compartment. That was just an expression. Expression of what? A figure of speech. I was trying to tell him that we'd be working late. Oh, then to burn the midnight oil implies late work. That's right. I'm curious, what is the etymology of that idiom? How did it come to be used in contemporary language? I don't know, sir.
Commander Data, welcome on board. It's so very good to see you.
It is good to see you too, sir.
I could use your help with the infuser array.
Certainly.
As you can see, we're having problems with the plasma conduits.
This will need a completely new field induction subprocessor. It appears we will be required to ignite the midnight petroleum, sir.
So Data can do many of the things that humans can do. Some things he can do even better. And when you think about how amazing humans are, that's pretty good going. Now when you prepare a talk like this, it's very difficult, right, to know what audience you're going to get. So we're going to have a go at doing something, right, and you have to patronize me a little bit here, right, because I've done this with 19-year-olds. Most of you are older than 19, but we'll try it anyway, all right? And most of the people I've done this with have been from Wales, but the first language is English. I don't know if everybody's first language here is English, but we'll try. What we're going to do is a little exercise where everybody's going to take part. I'm going to count up to 3, 1, 2, 3, I'm going to hit the button, and then what's going to appear on the screen is some text, and then we're going to read it out aloud together. Everybody up for that? Yes. Alright. 1, 2, 3. I couldn't believe that I could actually, we're supposed to read this out together, right? Listen, listen up. 1, 2, 3, hit the button, it comes up, we all read it out together. 1, 2, 3. I couldn't believe that I could actually understand what I was reading. The phenomenal power of the human mind. According to research at Cambridge University, it doesn't matter in what order the letters in a word are, the only important thing is that the first and last letters be in the right place. The rest can be a total mess and you can still read it without a problem. This is because the human mind does not read every letter by itself, but the word as a whole. Amazing. And I always thought spelling was important. Now, we're going to have a look at 4 very simple techniques. The first one has probably very little to do with some of the things that we're talking about in this conference, but it just helps set the scene really for some of the things data needs to be able to do. There we have a black and white photograph. Now, we know that that's not really a black and white photograph, because what we have here is we have some very black areas and we have some very white areas, and in between the very black and the very white, what we have is a whole area of grey. And what we can do with our digital cameras and with our computer systems, we can have that map running from very black to very white, and then what we can do is that we can superimpose that a set of numbers, and then from then on we can do things mathematically. So for example, we have 2 main objects there on a white background with a little bit of noise that's come out in our image, and what we can do is we can very simply digitize it, where we've taken those pixel values, those grey levels, and now we've superimposed on those numbers. And from then on what we can do is very simple mathematics. So for example, one of the things that we can do is threshold, where we can put all the values that are greater than a threshold value to be black, all the pixel values that are less than the threshold value to another value. And then what we can do is we can use some very simple image processing techniques to work out how many objects we've got in that scene. We can use very simple image processing techniques to work out what those objects are. So for example, here what we're doing is going through and we're giving each non-zero pixel unique value. And then what we can do once we've done that, we can run another little filter through, which allows us to count out how many objects there are, and we can work out that we've got 2. And then what we can do is that we can use various techniques such as template matching to take that object that we've got in our scene and to match it with objects in a database of objects that we've already learned, and we can work out and identify what that object is. Obviously things are a little bit more complicated. Certain objects, as we get nearer to them, they appear smaller the further we go away, larger as we go near, and so we have to match and scale those things before we actually do that template matching. But basically, computer vision is a field that is pretty well established these days. I've already touched on in the previous talk neural networks, and the image processing that we've looked at is achieved using algorithms, and we use algorithms in everyday life to do all manner of things. Where we have a process that we want to achieve, we have an algorithm that allows us to achieve that process, and we have a typical step in that algorithm. And if we follow through that algorithm step by step, hopefully we should achieve what we want to achieve. Now, that's not the way that brains do things in a completely different way. And neural networks are attempts to do the things with a computer in a similar way to which the brain does things. And the emphasis is on a similar way. The brain does things in a remarkable way, but a neural network is just a simple example of how a very simple brain might work. Here's a little example. We've got two inputs, input 1, input 2, and basically what we want to try and do is get this simple node, a single cell in a neural network, to learn something. And basically what we do is that we have these two things which we call weights, and we have this thing here which we call a threshold. And basically what we do is we take each input pair at a time, we pass it through, we multiply it by the weights, we add the things together, we compare the output with the threshold, and if the input is greater than the threshold, then we output 1, else we output a 0. We do that for another pair of values, and again we might get something at the end, which happens to be right in this turn. We do the next pair, we keep doing this iteratively. Obviously that one's come out wrong, so we have to do something. Now the network needs to learn, and the possibilities for learning are to adjust the weights and to adjust the threshold. And we can increase the threshold, increase the weights that contribute to the error. And so we have a very simple learning algorithm where we can adjust the weights, adjust the threshold, until you end up in a situation where the outputs match the input. That is, the thing as learned. How might data use this bit of information? Let's imagine that Data's got an inbuilt music player in his brain, and basically what he wants to do is he wants to select the songs that he wants to listen to. So let's imagine Data has access to a store of 1 million song tracks, and he wants to download the ones that he might like onto his inbuilt player. And obviously he's not got the time to listen to all the songs. Thus what he wants to do is a way of selecting only the songs that he's likely to like. He's going to use a neural network to do the selection. So the way that this might work is that first he selects 100 tunes at random from the 1 million that are available. They have already been classified, and Data just has to listen to them to decide whether he likes them. So they've been classified, he listens to it and he decides whether he likes it, whether he doesn't like it, or whether it's just plain awful. It's been categorized by the record producer or the music producer, and that's the categories that have been used. So, for example, if the song was a classic song, it would be classified as 0. If it was a ballad, and the style, it would be classified as 3. If the artist was a duet male, it would be classified as 5. And if it had a dance band feel, it would be classified as a 4 under that category there. Now what happens is that a singer from the UK, Leona Lewis, song that Data is going to listen to has been classified as 1 in the category, 3 in the style, 1 in the artist, and 1 in the accompaniment, and Data listens to it and he says, I love it. We might do that for some other songs, so we do it for the 100 songs that were selected at random. And then once that's happened, what we would do is we would train a neural network. Here we have the categories that are coming in to the neural network. The network would make a prediction whether Data would love it or not like it. If the network gets it wrong, then what we have to do is we adjust the weights appropriately, so that over a period of time, what would happen is that the neural network would learn songs that Data liked, thought were awful, or was indifferent to. The training routine is repeated many hundreds of times using the 100 randomly selected songs, and And hopefully now the neural network should know the kind of music that data likes. The neural network could then quickly go through the other 990,000 songs and pick the ones that data is likely to like. And then those songs can be simply downloaded for him to listen to. So Gareth Gates is another singer from the UK. What we do is we pass the categories, the style, the artist, the accompaniment that the record producers have given that song through the neural network, and we work out whether data is likely to like it or not. The second kind of thing that data might use is a genetic algorithm. So let's imagine that data, how might he use a genetic algorithm? Let's imagine that data lives on that planet there, and what he wants to do is he wants to go and visit his friend. So he lives on the red planet and he wants to go and visit his friend on the green planet. There's simple a route from red to green and then back home to the red planet. That's easy enough. If he wanted to go and visit a friend on the second planet, the blue planet, then the issue is that he has two possible routes now that he might take. And what we can do is, using this simple distance chart here, we can work out the length of the route that data needs to travel. And so the route there is 42 units, whatever that unit measurement is. Now the issue is that he could also go the other route. He could go from the red to the blue to the green and then home. And as you can see there, the alternate route is the same distance as the first route. The issue happens when data wants to go and visit friends on lots of different planets. Just visiting friends on those planets, there are 5,040 possible routes. And the issue there is that not all the routes are the same length. Now, it would be very quick to do a little calculations, write a little program to do the maths that would work out which was the possible, which was the shortest route there. That wouldn't be an issue at all. But, so we can see the routes are the same, and we can work out very quickly which was the quickest. The problem is that as the number of planets to be visited increase, so the possible routes increase at a very, very significant rate. So by the time we get to 20 planets, the number of options in terms of routes becomes so high that it's impossible for us with a modern day computer to work out that best route very quickly. So how might data use a genetic algorithm? Well, let's have a look at this as a family resemblance. That fella was voted the most influential father in the United States 3 years ago. His name is Homer Simpson. And what we could do for Homer Simpson is we could extract from Homer characteristics that made up his features. So we could extract information about his height, his hair colour, his eye colour, and we could put that into a code. We could also take that code and then put it together. So now we have Homer, the real person, who is the phenotype in terms of genetic algorithms, terminology, and we have the genotype, which are the string of zeros and ones that actually represent him. That's his wife, Marge. And what we could do for Marge is we could do the same thing. We could extract the information from Marge and we could put together the genotype that represented the phenotype. The actual character, Marge, the genotype, the strings of 1 and zeros. Now, they've had children together, and what happened when they had children together, to cut a long story short, is that part of the genotype from Homer got mixed into the genotype from Marge, his wife, and then that could be translated back to individual components that make up their son, Huang. Now, He has a phenotype, he has a genotype. Part of the genotype came from his father, part of the genotype came from his mother. Now, family resemblance. What would happen if tall people always married tall people and had children together? Short people always married short people and had children together. Now, over a number of generations, what we would find is that there might be still some people who are average height, but by and large, people would become very tall and people would become very small, shorter. There would be a divergence. Now, we can use that bit of information to help us. Here we have 5,040 possible routes. Blue route, the purplish route, the greenish route. And what we do with genetic algorithms is basically we have a look at a very small subset of all possible routes. So here we have a population has 6 individual routes. In reality, we would use more like 100. And we pick the shortest 2 routes and allow them into the next generation and also breed with them. And the way that we breed is exactly the same as we did with March and Homer, is that we take part of each and we mix them together. And remarkably, what we find is over a number of generations is that the shortest route decreases significantly. And genetic algorithms is just one of a whole number of what we call optimization algorithms. And these optimization algorithms have been used in a huge variety of fields to actually go from a huge possibility of possibilities down to some that are manageable. The final one I want to talk about very briefly is expert systems. Expert systems is probably the most common, well-known and most successful to date AI technique. Here we have our expert, or he thinks he is an expert, as our UK Prime Minister. What we have is an acquisition module, which is the means of getting the expertise from the expert into a way that we can understand. Getting expertise from an expert is notoriously difficult. What makes an expert is very difficult. Sometimes you see these books, how to make £1 million in a week, you know, go and buy it and I'll tell you my story. In reality, if it was as good as it says it was, you'd be making millions, not writing books. But getting that information from the expert isn't easy. Then we have this knowledge base where we store the expert's information in a way that we can use. Then we have this thing called the Inference Engine, and we have the user. So, when I was in school in the UK, we learned something called the Green Cross Code, which is what we used to use when we crossed the road. And basically the Green Cross Code said this: when you cross the road, look right, look left, look right again, and if the road is clear, then cross the road. Other things we learned in school that were of interest: remember that in the US they drive on the wrong side of the road. Things we picked up in school. So all that kind of knowledge would be in the knowledge base that we have. Now, what happens when data goes on his US holiday? He's got that information that he's learnt, those rules, they've been taken, they've been put into that rule base. He needs to cross the road, please advise. What would happen is he would look at in the rule base. The rule base says when you cross the road, look right, look left again, and if the road is clear, cross the road. It would also flag that, remember, in the US, they drive on the wrong side of the road. And so what would happen is that the expert system would give the advice: look left, look right, look left again, and if the road is clear, cross the road. So it's taken the things that are in its knowledge base and it's combined them together in a new situation to give new advice that helps solve a new problem. So bringing it all together, what is likely to happen, or one scenario of what could happen, is that if data is to ever accomplish what he accomplishes in that program, then it's likely that he's going to have lots of different techniques that are used and brought together to actually achieve what he wants to achieve. And I think one of the things that's of interest to me at this conference is how some of these techniques might be used in new areas, in new ways, brought together in new combinations in a way that makes sense to actually do something that's of interest. So, thanks for listening.